Vaishnavi. I'm pursuing fourth year BTech in Electronics and Communication Engineering at CMA Technical Campus, Hyderabad. Today, I'm going to present my Embedded System Internship Project on EV ADAS dashboard using STM32, Bluepill and PICSimLab. Here we go. My agenda is to introduce about embedded systems and project overview and objective, what I have learned from this internship and how I gained the experience, what about all tools used here, problem statement and solution approach, and also system architecture and data flow, tools and technologies used, STM32 development and peripheral configuration, EV controller implementation, ADAS features, UART communication and Python dashboard, how I tested and results and demonstrations, and how I faced the challenges, how I learned what are the outcomes, conclusion, and future steps. Here we go introduction or project overview. First of all, about EV ADAS. Our EV ADAS dashboard system is first of all EV means electric vehicles. This generates the large amount of real-time data such as vehicle speed, battery, SOC, system on chip or state of charge, motor temperature, torque and range. Next, ADAS. ADAS means Advanced Driver Assistance Systems. This improves the vehicle safety by detecting like collision risks, blind spot vehicles, nearby obstacles. This project develops a real-time EV monitoring and ADAS safety system using STM32 F103C86 Blueprint, PICSimLab Simulation Environment, UART Communication, Python based dashboard. Here we see the system architecture. Here we go. First, we use sensors like simulator or potentiometers, acceleration pedal, brake pedal, temperature, SOC. This acceleration pedal PA0, brake pedal is PA1, temperature is PA3, SOC is PA4, PA0, PA1, PA2, PA3. Sorry, I got STM32 Blueprint. EV control, ADAS engine, fault handler. Next, UART communication. Here we use baud rate as 11 tau 11 5 200 bps. Next, by Python dashboard, speedometer, SOC bar, and dashboard IV. Here we go how the problem statements and solutions occur. The problem statements are modern electric vehicles, how generate the huge amounts of real-time data, and monitoring the continuous range need like speed, battery, SOC, motor temperature, torque, and range in parameter like these parameters. And monitoring multiple vehicle parameters is difficult manually. So safety risks like collisions, blind spots, and fault need quick detection. For this, I have found solutions. Those solutions are developed a real-time EV ADAS dashboard system, STM32 Bluepill. This collects the process and vehicle sensor data, and ADAS features detects the forward collision warning. It detects the warnings, blind spot detections. Next, parking assist. Like car, we have in real time, we'll take car as an example. Next, Python Dash provides live visualization of EV parameters and alerts. And here we go to next slide. Those we have used tools and technologies. What are the tools and technologies we used in this slide? I would explain. Software tools like STM32 Cube IDE, STM32 firmware development, GPIO, next ADC, timer, UART configurations, next PICSimLab, STM32 Bluepill simulation, sensor and LED testing, Python 3 dashboard development, next Python libraries, Matplotlib, dashboard visualization, NumPy, data processing, PySerial for UART communication. Next, here we use hardware components like STM32F103C86 Blueprint, HCSR04 ultrasonic sensors, potentiometers, ADAS simulation, LEDs for alarm indications, UART serial communication. Here we see the simulation setup of STM32 development at PICSimLab. The host is laptop. Here we go from laptop STM32 cube ID. We write the code in embedded C language. Next we build the files in .x and .binary. Then we upload the binary file in PICSimLab. Then we to here we upload the file and we see the output. We connect the all those connections which are taken and implementing then in UART output. In UART output, we will arrange the baud rate as 11.5 bps. Next, I have implemented Python UV dashboard. Next, sensor integration and data acquisition. Here we use the module spare parts. These are the module spare parts in PICSimLab. Uh, those parts are this is potentiometer. Potentiometers are ADC, acceleration pedal input, brake pedal input, battery source simulation, water temperature monitoring. Next, uh, here we use IO virtual term and also ultrasonic sensors. One is front obstacle detection, left blind spot detection, right blind spot detection. Here we use some formulas for EV control and vehicle dynamic models. Um, in this internship, I have gained some knowledge on this vehicle dynamic models and by learning about formulas and by executing them. Here we go. What are the formulas we have used? Basic formula on speed calculation, like speed is equals to distance by time. Vehicle simulation, V is equals to V initial plus A into T. V final speed, A acceleration, T time interval. Ultrasonic distance measurement, distance is equals to time into speed of sound by 2. So for example, we take echo time in microseconds. Echo time is 1000 microseconds, and we have taken 0.0343 as sound speed of sound by divided by 2. So final answer is 17.15 centimeter. Next, timer calculation. Here we use timer 2. Timer frequency is clock frequency by prescaler by 1. Clock is 72 megahertz, prescaler is 71. Timer frequency is equals to clock is 72 and by prescaler rate is 71 plus 1. So 1 megahertz. Next, time to collision is equals to distance by relative speed. Example, distance I have taken 50 centimeters. Speed is 10 meters per second. The final answer is 0.05 seconds. Here we see threshold like T, time to collision is less than 3 seconds. It is a warning. If it is less than 1.5 seconds, then it is critical. Battery SOC estimation. SOC new is equals to SOC old minus power consumption into time. Next, region braking. In regenerated energies, SOC new is equals to SOC old plus regenerated energy. Here some ADAS features and safety system. Here I have taken the car as real-time example. We can see how the features and safety system here we use. Advanced driver assistance system ADAS. Here forward collision warning FCW. Front HC SR04 ultrasonic sensor continuously monitors obstacles and distance and time to collision are calculated. If alarm levels are less than 50 centimeter distance, then it is warning. If it is less than 20 centimeter, it is critical. Next, blind spot detection. Left and right ultrasonic sensors detect nearby vehicles. It will detect the nearby vehicles, left and right. Here you can see left and right surround views. Um, Forward views as cross traffic alert, part assist, traffic sign recognition, lane departure warning, emergency braking, pedestrian detection, collision avoidance. Next, adaptive cruise control. Here we can see color and color indications. Pink, radar, leader, camera, ultrasound. So, left and right are blind spot detection. For front is forward collision. Next, parking assist. Parking assist means it active low at speed when it is less than 10 km per hour. It provides proximity warning. It provides warning at three ultrasonic sensors. Here we can see back view, blind spot detection, rear collision warning, park assist, surround view. Next slide. Here in this internship, I have implemented many projects like Blink LED, ADC test, EV dash, next ADAS, UART, FSM, ultrasonic timers. These are the projects we have implemented, and the major project is about Python EV dashboard. Here we see timer and UART communication. Timer 2 used for ultrasonic timing. Next prescaler have taken is 71. Here we use 1 microseconds is timer resolution. In UART, transmitter is APA9, receiver is PA10, and we can take baud rate as 11, 5 to 100. Next slide about pin configuration on timer and UART. We can see the pin configuration, how they connected, how we implemented, and time. This is the timer, this is the UART. Here we have taken timer 1, timer 2, timer 3. Here we have taken UART 1. See, these are the pins. See, green color. They are connected. Next slide. Python EV dashboard test. Next, testing and results. In Python EV dashboard, some features are there: speedometer, battery sourcing bar, EV metrics, ADAS bird eye view, alarm display, libraries like Matplotlib, NumPy for data processing, PySerial for serial communications. Testing and results. Testing and results like we tested and result and what we have checked the results. What are the output we have gained like this? The dashboard received UART data, speed and SOC values displayed, alarm conditions tested, LEDs tested in PICSimLab, sensor data visualization verified. Next, here I will show the demo of Python EV dashboard. Then this is the code of Python EV dashboard. So from here we go to command prompt. I open my command prompt and I open the project folder. Next I run the dashboard using this command ev dashboard.py demo. Then it will open the Python dashboard. See here we see the speed, and speed history, alarm conditions, mode, EV metrics. When it is decreasing, it becomes critical. When it is decreases, when it increases, it becomes normal and advisory. When it is in middle of the speed, it will become advisory. Here I have implemented on critical. Next, I will show the here is PICSimLab. This is the PICSimLab. When we can change the values, Here I change the values. Front distance, right distance, left distance. So the LEDs go went on. When I increase or decrease, then the LEDs goes off. Python is showing critical. This time I will show some projects I have implemented. Here it is ADC test. This is the code of the ADC. Here we have implemented 200 radar sensors. Next, blink LED. In blink LED, we have taken pin 13 as a GPIO return pin, and it is a reset. Here we go. We have delayed for 100, like 1 second. Next, have implemented EV dash. Timer 1 second. Timer. So here I have taken PICScaler as 7199 in this timer, and in init period 999, and this is timer 1 second. Next I have implemented ultrasonic sensors. Have gained some knowledge on this, how to write the code and how to implement this, how to detect them, how we use sensor, and how we connect each other. Here in this main.c ultrasonic sensor, I have taken printf and distance as ultrasonic read 100 milliseconds delay. Next, here I have taken in prescaler as 0, period as 65535. Next, I have done my assignment on ultrasonic 3 sensors. Using 3 sensors, I will show this. This is the ultrasonic 3 sensors project main.c. Here I have taken D1, D2, D3 as my full load values. Here we see that D1, D2, D3 as pin 0, 2, 4, 2, 4, and output pin as 0, input pin as 1, 2, 3, D2 as 2, 3, D3 as 4, 5, like this. Here we use 500 millisecond delay. Here I have taken say prescaler as 0, 65535, and I will show the output of this project. I have taken the screenshot of this project. I will show in my desktop ultrasonic assignment output. So this is the output. And I have open PICSimLab file, upload load binary file, and I have taken modules, spare parts, and I have taken some ultrasonics 3 sensors, friend like 1, 2, 3 sensors, and this is Algo virtual turn, it shows the output. Here we can see the output. This is my assignment I have completed in this project. And this is the unit Python dashboard. I have learned from this project many things like alarm conditions, three conditions like normal, advisory, critical. When it is normal, then it is safe. When it is critical, like it is in danger. Advisory means some like it's warning. So we'll see the conclusion. So here I will conclude that I have learned STM32, embedded programming, GPIO, ADC timers, UART concepts, sensor interfacing, Python dashboard development, real-time embedded system workflow. Next, here feature scope is one can CAL communication, real vehicle sensors, hardware prototype, hardware prototype. Sorry. Here when in PICSimLab, when I change the values like sensor values, it will be it will read the values, process them, and change the telemetry. UART communication. The Python dashboard automatically updates without restarting it. Next, this is my project. Here we go. Uh, I have when the obstacle distance decreases, the value warning level changes. Similarly, when battery becomes temperature cross the threshold, the dashboard shows different alarm levels like warning, critical, advisory. This demonstrates the real-time communication between STM32, Bluetooth, PICSimLab, UART, and Python dashboard. Here we go. I will conclude that what I have learned from this internship, how it is, how I gained. This internship helped me a lot, and I have gained my practical experience in embedded systems, STM32 programming, UART communication, real-time dashboard development, and debugging. Thank you. Thank you.